Okay, welcome to this explainer. Let's get straight into it. Today, we are mastering Cambridge IGCSE physics, specifically syllabus code 0625, focusing on ultrasound. But listen, we are not going to tackle this by cracking open a textbook and reading dusty definitions. Absolutely not. Instead, we're adopting the mindset of a jazz musician. Think about it. The greatest jazz musicians on earth improvise beautifully, right? But they can only break the rules and create magic because they have entirely mastered the underlying scales and structures first. You have to know the rules before you can break them creatively. In physics exams, your scales are the core structures of how you answer a question. Imagine you're sitting in the exam hall. The clock is ticking. You flip to a heavy 10-mark structured question on ultrasound. I want you to meet two types of students we see all the time. First, there's Alex. Alex is a textbook walking. He overloads his answers with raw physics facts, dumping formulas onto the page with zero actual analysis. Then there's Sam. Sam panics, rushes through the paper, completely misses the specific command word requirements, and writes a vague story instead of a scientific explanation. If we put their exam papers side by side, it is just a sea of red pen marks from the examiner. Today, we are going to fix that. We're going to completely flip the script, look at how ultrasound appears in real systems, run through actual exam calculations, and build your physics success blueprint. So here is our roadmap for today. We'll start with the ultrasound hook, move into a 4-step walkthrough, deep dive into physics, cause and effect, explore real-world applications, focus strictly through the exam lens, and wrap up with active memory prompts. It is a highly structured pathway taking you from basic curiosity straight to exam readiness. All right, section 1, the ultrasound hook. Let's look at the challenge at hand. Normally, a lesson on waves and sound might start with a super dry definition, right? Something like, ultrasound is sound with a frequency greater than 20,000 hertz. But honestly, starting there makes the whole concept feel decorative. It encourages you to just memorize rather than reason. Let's look back at our student Alex. Faced with a Cambridge past paper question asking to explain how ultrasound is used to find the depth of the ocean, Alex just writes, ultrasound is over 20,000 hertz, V equals F lambda. And that's it. 0 marks for application. Then there's Sam. Sam writes, the boat sends a sound down and it bounces off the bottom so they know how deep it is. Again, barely scraping a single mark because there is no physics terminology there. Instead, I want you to ask yourself, what physical effect, measurement, or prediction actually depends on understanding ultrasound? Framing it this way makes the physics absolutely necessary. Before we even touch the formal mathematical language, we want to ask ourselves, what problems in the real world can only be solved if we understand these incredibly high-frequency waves? This approach makes you far less dependent on memorized wording and so much more capable of reasoning your way through those tricky, unfamiliar exam scenarios that they love to throw at you. Okay, moving on to section 2, the 4-step walkthrough. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's reveal the strategy. Once we are hooked on the concept, we need a reliable framework. In Cambridge exams, top students structure their answers using the PEEL framework: point, evidence, explanation, link. And we can map that directly onto these 4 steps for tackling any ultrasound question. Step 1, identify the quantity or phenomenon. That's your point. For example, pointing out that a high-frequency wave is echoing off a boundary. Step 2, state the relationship involved. That is your evidence. You bring in the classic speed equals distance over time equation. Step 3, explain the underlying physics in clear terms. This is crucial for your explanation mark. You have to explicitly state that because the wave travels to the seabed and back, the distance traveled is actually double the depth. It's 2D, not just D. And step 4, connect to an observation or real device. That's your link. I'm giving you 30 seconds right now. Look at these steps. Can you spot which parts Alex and Sam completely missed earlier? Yeah, Alex completely missed the explanation and the link. He just dumped evidence. Sam gave a weak link but completely missed the point and the evidence. Neither followed the PEEL framework, and that's why they lost marks. Let's move to section 3, physics, cause and effect. This is where the magic happens and the transformation begins. Okay, we've got a visual timer running for 60 seconds. We are going to rewrite Alex's answer live, turning those red pen marks into green check marks. We need to transition from everyday language into specific mechanics and physics vocabulary. To build this vocabulary, we always begin with a concrete example. Imagine an ultrasound wave hitting a boundary, like a microscopic crack hidden deep inside a solid block of metal. When the wave hits that change in density, it reflects. Only when you really grasp that physical reality should you introduce symbolic relationships. In an exam, if they give you an oscilloscope graph, a spike on that screen isn't just an abstract geometric line. It physically represents an echo returning over a specific time delay. So for Alex's rewrite, instead of just dumping a formula, we write, the ultrasound pulse is emitted, travels through the material, and reflects off the boundary. The time delay t between emission and detection is measured. Using speed equals distance over time, we calculate the total distance. Since the pulse travels there and back, the depth is half of this total distance. Boom! Maximum marks. Grounding abstract concepts in reality is the blueprint for physics success. Every single line on a graph represents something happening in the physical world. Now, let's look at Sam. Sam rushes and ignores command words. If a question says, explain, you cannot just state. The overarching philosophy here, our golden rule, is this. Insist on cause and effect rather than isolated facts. Whether you're dealing with waves, fields, or forces, reasoning always trumps memorizing isolated data points. For example, if a wave enters a denser medium, its speed changes, and as a result, its wavelength changes, but its frequency remains constant. Why? Because the source of the vibration hasn't changed. That is the physics cause, bridging the effect. If Sam just memorizes that wavelength goes down, a slightly reworded exam question asking why it happens will trip him up completely. By insisting on cause and effect, you build an unbreakable chain of logic in your answer. You are improvising within the structure, just like our jazz musician. You can adapt to literally anything the Cambridge examiners throw your way.
Let's step into Section 4, Real-World Applications.
Stop scrolling! Subscribe to our YouTube channel, Ace the Exams and AceTheExams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to AceTheExams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, we are stepping outside the classroom right now for our interactive workshop. Ideas from Ultrasound don't just live in 0625 textbooks, they are literally keeping us alive and safe. Engineering, medical technology, transport. Let's do challenge 1, the data scan. I am putting a 60-second visual timer on the screen. Imagine you are looking at a complex data table showing the acoustic impedance of different human tissues, bone, muscle, fat. The exam asks why gel is used in medical ultrasound. Your 60 seconds are ticking. You have to extract the core trend. What's the physics reason? Time's up. The answer? It's about safety and medical technology. Without the gel, the difference in density between the air and the skin is so huge that almost all the ultrasound waves would instantly reflect off the surface of the patient's body. The gel acts as a coupling medium, matching the impedance so the waves actually enter the body to give us an image of a baby or check an organ. We use these physics rules to solve massive real-world problems. Let's switch gears to Section 5, the exam lens. It is time to translate our cause and effect understanding into cold, hard marks. This brings us to Challenge 2, Find the Flaw. I'm going to read a flawed sample paragraph from our rushing student Sam, and you have to find the exact sentence that loses the marks. Here is Sam's answer for how we find flaws in metal pipes. We shoot ultrasound into the pipe. The sound travels at a constant speed, it hits a crack and bounces back to the start. So we know where the crack is by looking at the time. All right, timer is running. Where is the flaw? Got it? Sam missed step 2 and 3 from our framework entirely. Sam gave a vague definition and application, but where is the relationship? Where is the mathematical explanation? To get top marks, Sam needed to write, using the relationship distance equals speed multiplied by time, and knowing the speed of sound in the metal, we have the total time recorded because the wave traveled to the crack and back. This structured 4-step approach, definition, relationship, explanation, application, is the safest method for structuring your exam answers. I am going to issue a direct examiner warning here. If you look at the left side of this comparison, this is what loses grades every single year. Writing formulas without defining the variables, or quoting processes like saying, ultrasound is used for cleaning without explaining the physical link. Now look at the right side, grounding examples in a clear cause and effect chain. This brings us to Challenge 3, speed writing. You have 30 seconds to mentally write one perfect peel paragraph explaining ultrasound cleaning. Ready? Go. Timer taken down your head. Okay, time's up. A perfect answer on the right side looks like this. Point. Ultrasound is used to clean delicate machinery. Evidence. Waves above 20,000 Hz are directed into a liquid bath. Explanation. These high-frequency waves cause rapid, localized pressure changes, creating tiny bubbles that physically blast dirt away from the object. Link. This physical vibration cleans complex shapes without damaging them. See the difference? You connect the dots for the examiner. You don't just state facts, you explain the physical mechanism.
Almost at the finish line. Section 6, Active Memory Prompts.
Let's lock this final system in. Reviewing your notes by passively reading them is a massive waste of time. You have to actively prompt your memory. To hit 100% mark potential, we use 3 rules: command word decoding, the Peel framework application, and the time management matrix. And you drive those 3 rules using these 4 specific active memory prompts. Ask yourself aloud right now, what is the core idea of ultrasound? It's sound waves with frequencies above human hearing. What changes physically? They reflect off boundaries between different densities. What quantity or graph shows it? An oscilloscope trace showing time delays between the emitted pulse and the echo spikes. And where is it used? Non-destructive testing and medical imaging. If you can confidently answer these 4 prompts out loud, your grasp on the topic is completely secure.
Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Before I go, I leave you with this provocative thought to test your mastery. Don't just memorize the definitions tonight. Can you actually build the chain? Can you take any real-world application, break down the physical cause and effect, define the variables, and explain it clearly like a jazz musician improvising a perfect solo? When you can do that, you haven't just memorized physics. You have learned how to think like a true physicist. Keep asking why things happen, and I'll see you in the next one.